Hi, I'm Zhang Boyao, the first author of this poster. I'm advised by Professor Jiankun Li at Programming Language Lab, PL Lab, at the Department of Computer Science, National Tsinghua University, Hsinchu, Taiwan. Here's the outline of this talk. We're going to go through motivation, objective, rewriting in TVM, experiment, ongoing work, and summary. So, parallelism technical specification was merged into C++ 17 and 20. Let's take a detour to look at C++ release model. Ever since C++ 11, the committee adopted the so-called trend model. They standardize what's fully baked and iterate on immature features and proposals. This is very similar to how LLVM operates. All development happens on the main branch. A release branch is then created twice a year at the release manager's discretion. After some testing and cherry picking, a release is then created. So a time-based instead of a feature-based release model is adopted. So the parallelism TS proposed by NVIDIA folks brings some parallel algorithms to C++, and which we want to incorporate into TVM generated kernel code. So let's look at what's TVM. TVM is an AI framework. It consumes a computational graph depicted as the figure on the left. So it consumes a computational graph, such as the one on the right, and it do some computation, do some optimization on it, and finally the coding module would consume the TVM internal representation (TIR), which and the outputs in this case an OpenCL kernel. So our objective is to transform this for loop on the top into stud for each n, with the first argument being stud execution on SYC. So with this argument, we hope this for each n is vectorized. And the second argument came from 0 is a helper. It is a helper iterator, comes from 0. This is the come from 0 definition, which comes from 0 and provides prefix increment and a dereference operator. This is the rewriting done in TVM coding modules. So the loop body is a single one-liner assignment expression, which is represented as a store node inside TVM internal representation. So we check if so when traversing the TVM internal representation, when we encounter a for node, we check if the loop body is a store node, which corresponds to 169. And if so, we output stud for each n and stud execution on SYC and the like. Next, the rewriting done for accommodating SPIR-V compilation flow. So first, we prepend to include directives to the just generated kernel code. and then write it to a file called filename.clcpp. And then we invoke clan to compile the source code into a vectorized LLVM bitcode. And then LLVM SPIR-V would translate that into a SPIR-V binary, which is to be consumed by CL create program with IL. So contrary to what was previously used, the CL create program with source, we use CL create program with IL here. And the experiment environment, we use clan 13.0.1 for compiling the text file into LLVM bitcode. And the LLVM and the SPIR-V translator is the a patched LLVM SPIR-V built against LLVM 13.0.1. The OpenCL device used is Intel HD graphics 630, and the OpenCL version is 3.0. The TVM we use is based on this commit hash. Next is the LLVM SPIR-V workaround. The official LLVM SPIR-V can handle freeze instruction. So basically some optimized LLVM SPIR-V binary, some optimized source code will turn into some bitcode containing freeze instruction. So we work around it as Intel does, adding these lines. Here's the speed up after vectorization. So we can see a high of 38% speed up and a low of 6% speed up. The base version is the stud for each end without the unsick execution policy. And the vectorized version means we specify unsick as the first argument. And we have some ongoing work here. We want to provide layout and view for sparse abstractions for TVM with C++ for OpenCL. It's basically a class template parameterized with sparse matrix compression format, such as this slide. We want to abstract some computations away into a class template called view and parameterized with a like CSR format at the bottom. To sum up, we C++ify TVM generated OpenCL kernels inspired by the parallelism TS. Building upon our work from last year, which is bringing C++ unsequenced execution policy to OpenCL kernel, we put unsick into TVM generated code by identifying a store node in the loop body and transform the loop. Neither does performance improve significantly, nor does it degrade. The ongoing work to provide layout and view abstraction to help facilitate sparse computations for TVM and investigating TVM backends with more kernels APIs is of interest. Thanks for your time.